Since both the valves are open, are in the open condition, and you have a gradient available for the flow of exhaust gas into intake manifold is going to take place. The problem with this backflow, and this problem is more severe at low load condition, because at low load you will have a considerably lower pressure in the intake system. I think we have already discussed about this. This backflow of exhaust gas, what it will do, there are two effects. One is it is going to reduce the temperature of the mixture. Okay, temperature of the mixture is reduced due to the components present in the exhaust gas. The components present in the exhaust gas are triatomic gases, primarily H2O. Atomic, there are three atoms, as you could notice. These triatomic gases have very high specific heat. You know, any high specific heat component won't increase the combustion temperature. It will absorb the heat that is released during the combustion. It won't allow the temperature to rise. So one of the important effects is drop in temperature during the combustion event. Okay, and the other important effect, when there is a reverse flow, it displaces the fresh air. Since it displaces fresh air, there is a considerable drop in oxygen. Okay, so you have a lower temperature, you have a lower oxygen when the mixture is diluted. Okay, so this diluted mixture, what it will do is it is going to reduce the temperature during the combustion period, and because of that you cannot maintain a stable flame. So flame stability will get affected. Okay, especially during later part of expansion stroke, and when the combustion gets started late. If you have a late combustion, okay, the flame during the expansion stroke will lose its stability, because you have lower temperature due to the diluted mixture, and there is a lower oxygen content in the cylinder. So when the flame moves towards the unburned mixture, so this mixture, unburned mixture, is at a very low temperature. So here you have burned gas, here you have unburned gas, you have flame propagating towards the unburned mixture. Okay, since the temperature is considerably low compared to undiluted mixture, the temperature with the diluted mixture is going to be considerably low. Okay, so during the expansion stroke, when the flame moves towards the unburned mixture to burn it, okay, that since the temperatures are considerably low, the heat loss from the flame zone, chemical reaction zone, is going to be high. You know what is the condition for flame quenching? When heat loss is higher than the heat that is released, the flame cannot survive. So here the flame is quenched inside the cylinder itself, in the core region. Inside the core region itself, the flame gets quenched. So we talked about flame wall quenching, that is happening around the boundary. Near the wall, the flame will get quenched. So you will have less mixture that prevails around the wall region is unburned. This is what is happening with the flame wall quenching. But what we are talking now is bulk quenching. Bulk quenching means the flame is getting quenched in the core region, core combustion region. Now you can imagine the level of unburned mixture, because since the flame is quenched, you will have a large proportion of unburned fuel or mixture that will be carried away through the exhaust gas. Okay, during the exhaust period, you will have a very high level of SC that is happening. Fortunately, it happens only during certain conditions, during transient conditions wherein flame stability is very poor. Okay, so under those conditions, you will have this bulk quenching, okay, or misfire, because the flame is not available in the cylinder to ignite the mixture. So you will have a considerably high proportion of SC carried away through the exhaust gas. Clear? So these are the mechanisms for SC formation in a spark ignited engine. So now we are moving to CI engine, diesel engine. We are looking at SC formation mechanism in diesel engine. Please recollect that CO and NO formation mechanisms are same for SI and CI engine, because they are kinetically driven process. Unlike that, SC formation is based on the boundary layer fluid dynamics, which is going to be different for SI and CI engine. That's why we are discussing SC formation mechanism separately for SI engine and CI engine. Okay, so now we are going to look at the mechanisms that are involved to form HC in CA engine. As we have already discussed, HC levels in CA engines are considerably low compared to SI engine because they are not operated with rich mixture. Okay, overall equivalence ratio is lean on the lean side. So you use excess air, you have more air available in the cylinder, which reduces the overall total HC emission from the diesel engine. So HC, unlike NOx and particulate, it's not a major pollutant from CA engine, but nevertheless, we need to look at the mechanisms involved. Sometimes we also use after treatment control to reduce the level of HC in the CA engine. Based on the engine type and operating condition, HC levels may not comply with the current emission mandate. So you may have to control using some additional devices also. Thus, it is important to understand the mechanism behind HC formation in CA engine also. So that's what we are looking at here. So one of the HC formation sources in a CA engine, unlike SI engine, it is primarily due to mixture preparation. Okay, so you have a non-uniform mixture in a CA engine due to less time available for mixing. This is what we have already discussed. So the sources for HC formation in CA engine are primarily related to the mixing, fuel-air mixing. So as you could see here, one of the important source for forming HC in CA engine is over-mixing. Over-mixing of fuel-air mixture, what it will do is it will result in too lean mixture. So P will be very low, considerably low. Okay, so it will go lower than the lean limit. You have a rich fee limit, you have a lean fee limit. When there is over mixing, the value of fee will be lower than the lean limit. Thus, it cannot burn, rather it can only slowly oxidize. Okay, so partially oxidized HC will be carried away through the exhaust gas. And let us look at when this is happening in an engine operating cycle of CA engine. This happens during the ignition delay time. This happens, over mixing happens during the ignition delay time. Let us see how it is happening. When you inject fuel into the engine cylinder, okay, you have a core region where you have only fuel. So in this region, Phi is high, very high, or there are regions where Phi is infinite. What do you mean by infinite Phi?
Sir, 100% fuel.
No, only fuel. You don't have any air in that region. Any air, that's what I mean by Phi infinite. You don't have any air, you have only fuel present in those regions. Okay, so Phi is defined based on actual fuel by air ratio by stoichiometric fuel by air ratio. Air is in the denominator, so it is fuel divided by air. Air is 0, that's why Phi is infinite. So when I say Phi infinite, it's only fuel. There's no air at all. So when you spray fuel into the engine cylinder, in the core region, you may not have even air. There's no air at all. So you will have infinite Phi. Or there are regions where Phi is very, very high. Okay, meaning that the air levels are considerably low in the core region. Okay, liquid phase core region. Now, when you move in a radial direction from this core region, the outer periphery will start to form drops. I think we have already discussed about the mechanism. The outer periphery will be subjected to drop formation. It's like a film. So when the film breaks, how the film breaks? So you have a fuel film here, and that is breaking and forming drops. This is what we discussed, if you recollect, when we discussed about the delay time, ignition delay time. Okay. Now, what is governing this film breaker at the outer periphery?
Sir, fuel pressure.
Fuel pressure. More importantly, what is inside the cylinder at the time of fuel spraying fuel?
Air pressure.
Air.
So air is offering shear resistance. Because air is at higher pressure and temperature, right? So typical conditions I have already discussed, 30 bar and 700 K. This is a function of compression ratio of the engine. So when you spray fuel at high velocity due to high pressure, you have air inside the cylinder, and the air is offering resistance for the free movement of the fuel. We can say that this is offering some shear resistance for the free movement of the spray. Because of this shear resistance, the shear force offered by the air, the outer periphery fuel film will start to break and form drops, as you could see here. So because of this formation of drops, air will try to move inside this space, available space. So it will go inside the fuel region, try to occupy. That is how the air is entraining into the core region. Fuel spray region, right? Air will go and occupy based on the available space. Available space is based on the breakup of the film. If you have a continuous film, the air cannot even move inside. Did you understand? If you have a continuous film, the air cannot move inside. But what is happening? The film is broken and you have space available for the air to entrain. That's why after breakup, the immediate next process is air entrainment. If you recollect, this is what we discussed in the first chapter. Okay, so air moves in and the fuel vaporizes by taking the latent heat of air and get into the ignitable mixture proportion. By mixing with air, it has to reach the ignitable proportion. So what is happening when you move in this direction? This is a radial direction. When you move from the core spray region in a radial direction, you have a phi variation, right? Phi is subjected to vary when I move in the radial direction, because you have vaporization happening, you have air entrainment happening, you have mixing of fuel, vapor and air happening, everything is happening in this radial direction. So you have a distribution of phi in a radial direction. You have phi varying when you move in the radial direction. In the core region, it is very high. When I move towards, the phi will drop because you have air present in this region. So nearer to the core region, you have stoichiometric phi equal to 1 region. When you move further down, you're going to have more air with less vapor. Right? Outside this boundary, you will have only air. When you have only air, what will be the phi value?
0.
0. So outside this, you have only air where the phi is equal to 0. Now, nearer to phi equal to 0 region, you will have some fuel vapor present with very high air proportion. Okay, very high air proportion. This is what, that region is what is shown here with the shaded region. The shaded region is just nearer to phi 0 region, wherein the value of phi is much lower than 1. It's typically around 0.3 or less than that. So this is below the lean limit. So there is a rich limit for igniting the mixture. There is a lean limit for igniting the mixture. When you go below the lean limit, the mixture cannot ignite, right? The mixture can only oxidize slowly. This is what is happening in the shaded region. And this region is called lean flame blowout region. Nearer to phi equal to 0, you have a thin region with very less fuel vapor, very high air proportion. Typical phi value I've indicated here, it's around 0.3 or less than that. Since you have too much of air, you have that mixture below the lean flammability limit. Because of this, this mixture cannot ignite, it can only slowly oxidize. And thus, it has become one of the contributors for SC formation in CI engine, lean flame blowout region. And so what do you think are the parameters that will affect the thickness of the lean flame blowout region? So this region may be thin or thick based on certain parameters. So what are those parameters I'm asking?
But again, our pressures.
So this region, thickness of the region is a strong function of ignition delay time. When ignition delay time is longer, what will happen is more and more air will go and occupy that region. Did you understand what I'm saying? When the fuel quickly ignite, when the delay is shorter, the lean flame blowout region thickness will be less. It will be very thin. Okay, because ignition has started. But if ignition is delayed, when the delay time is longer, then you have more time available for pre-mixing. Did you understand what I am saying? So over-mixing is going to increase when the delay time is longer. Longer the delay time, more the over-mixing, meaning suppose if you assume that you have a pocket with phi equal to 1, when you give a longer delay time, this phi equal to 1 region is going to be filled in with air. So when you start filling in air, more and more air in the region where you have a stoichiometric proportion, what will happen to the phi value?
It will drop, sir.
It will drop. So that is what is happening. This blowout region is a strong function of ignition delay time. Longer the ignition delay time, more will be the lean flame blowout region, because you will have more lean regions inside the cylinder that is going to cause a higher value of SC emission. So this happens during the delay time, over mixing. You have too much air, very little fuel vapor, and that is a strong function of the duration of delay. Longer the delay, you have more pre-mixing, more air going into the region of fuel vapor, making it too lean to ignite. Okay, so this is what is happening with over mixing that contribute to SC emission. When I say that it's a function of ignition delay, it means it's a function of fuel, especially cetane number of fuel. When cetane number is less, you will have less over mixing because delay time is shorter. The pressure and temperature of the pressure and temperature inside the cylinder. When you have high pressure and temperature, you know delay time is going to. Another important parameter that affects is swirl. When swirl levels are high, you are going to have a shorter delay time. You know that because swirl, increase in swirl will reduce the physical delay time. Okay, so overall delay time will get reduced. So ignition delay is what is causing this SC emission through over mixing. If you could reduce the delay time, you will be able to reduce over mixing, and thereby you can bring down the SC level. So this is one of the important variable that causes SC emission in a CI engine. It's time up. I stop here. If you have any questions, I can take your questions.
Sir, this over mixing, in any case, due to this ignition delay, finally the fuel mass will accumulate and it will go for a knocking effect, no sir, like instantaneous combustion, no sir.
No. Knocking is okay. So what you are saying is when delay time is longer, there is also knocking.
Correct, sir. So in any case, my hydrocarbon is getting burnt, no sir. So like because the HC formation more or less should be the same irrespective of the accumulation, no sir. Because in any case, because only the phase is getting different, no sir. So more
No,
of
no, here your point is valid if you have a homogeneous mixture. If you understand the CA engine, the major problem is we have a heterogeneous mixture.
Okay.
So what you are saying is once ignition happen, everywhere there will be temperature will be high, and I'm going to burn this mixture also. That's what you are saying, right?
Yes, sir. Yes, because it is
what is happening here is totally different. If it is SI engine, you have a homogeneous mixture. Once ignition happen, everywhere the temperature will be more or less very high, and you will be able to burn everything. But what is happening in a CA engine, everything is happening locally. Okay, so even if there is a knocking, it's more limited to the local condition. Local condition it will affect. There are region you will have region with very low phi value, very low temperature value, because you will have a distribution of phi, distribution of temperature. Mixture is highly heterogeneous. If it is homogeneous, whatever you said is a valid point. But the problem with CI engine is it's highly heterogeneous, right? You will have knocking. You will also have a lean region that causes SC.
Okay, sir. Understood.
The problem is you have a 30 to 50% excess air.
Understood, sir. It's too of oxygen rich.
Yes.
Understood, sir.
In SI engine, if it is knocking, the temperature is more or less uniform everywhere. Locally, there is a very high temperature, but within the combustion chamber also, the temperature levels are high because you have a uniform phi. Unlike CI engine, you will have non-uniform phi. You locally have high temperature, high phi or rich phi, but there are regions wherein you have a too lean mixture with very less temperature that cannot completely burn.
Understood, sir. But sir, will this be dependent on the engine load also, sir? That means when I'm having less.
Engine load affects the delay time also, right? Whatever that affects delay time is going to affect the SC formation through this source, because at high load you will have a shorter delay, less over lean flame blowout region, but at low load you will have a longer delay. You will have more lean flame blowout region.
Understood. So in this case, this exhaust gas which comes out has more hydrocarbon, and we have more air also. So we can use this back for the EGR also, no, sir, for exhaust gas recirculation, so that we can enrich the mixture for my next cycle, because we have.
EGR composition is highly variable compared to SI engine. Here you have oxygen in the EGR.
Okay, sir. Okay, because we have hydrocarbons as well, and we have oxygen as well here, no, sir?
Yes,
It's
yes.
in a good proportion. My only question is that if the engine is turbocharged
Mm.
and if the exhaust gas recirculation comes back, then will this not excessively propel the turbocharger, sir? Because there might be some localized burning of fuel when this passes through the turbocharger, or will this be directly bypassing the turbocharger and coming into the inlet manifold, sir? If it is
No,
an
it
easier.
depends on where you are mixing with air. Okay, there are
Okay, sir.
two loops in turbocharger: high pressure loop and low pressure loop.
Okay,
Okay,
sir.
sometimes you mix the air and sometimes you mix EGR with air at the inlet to the turbocharger.
Okay,
Then
sir.
you will have a problem because you are taking exhaust gas to the turbocharger. The
Yes, sir.
other option is you mix the exhaust gas with air at the outlet of the turbocharger. Outlet of the, it is called high pressure loop because air leaving the turbocharger is at high pressure.
High pressure.
So EGR you are mixing with that air. Okay, so it means the turbocharger is clean because you are not letting out any exhaust gas to go into turbocharger.
Correct, sir.
Not turbocharger, I'm sorry, the compressor.
Compressor.
Okay,
Yes, sir.
turbocharger handles exhaust gas, compressor handles air.
Correct.
When you mix air and EGR at inlet to the compressor, compressor is handling a mixture of air and exhaust gas. This is called low pressure EGR loop. The other option is you mix EGR, that is exhaust gas, with air at the exit from the compressor.
Exit from compressor.
That is called high pressure loop because the air leaving the compressor is at high pressure. The only problem here is your exhaust gas pressure should be higher than the air pressure, then only mixing can happen. So you may have to use some blower to pressurize exhaust gas and mix it with air. But the advantage here is the compressor is handling clean air.
Understood, sir.
Whereas in the previous case, compressor is handling air gas mixture. Then you will have a problem with the turbocharger durability also. Understood, sir.
Understood, sir. Because why I was asking is, sir, one case, this drill ship, Deepwater Horizon, sir. This was an oil drill ship. So when the drill chuck broke and we called it as a moon pool. So when that got damaged, the gases came out with very high pressure from the deep sea, and it went into the inlet of turbochargers. So turbochargers propel the engines, and engines in fact reached more than twice the RPM, and that's why the explosion happened. So yes, sir. So because this is mainly because of very pure hydrocarbons availability for turbocharging. So when it enters into the compressor side, it propels the turbocharger to excessively more than 300%.
Yeah. The problem in having more unburned fuel in the exhaust is any hot spot in the exhaust line or in the intake line. Especially when you recirculate, it is going to create a severe problem, explosion kind of problem, because you have a fuel air ignitable mixture you are taking back to the intake.
Understood.
The problem, in fact, is more severe with hydrogen kind of fuel because they have a wide flammability limit. Gasoline or diesel is safe, highly safe from that perspective because they have a narrow flammability limit or ignitable limit.
Understood, sir. Understood, sir. It's clear, sir. Thank you, sir.
Okay, fine. Any other questions? Fine. So I'll stop here. I will meet you on Monday. Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thank you. Bye.
Thank you, sir.
Thanks.
Yeah. Thank you. Bye.
Thank you so much. Bye.